Hello, my name's Susan Pyne. I'm a postdoctoral researcher at University College London, and I'm going to talk about some work that I've done with Benjamin Joachimi, which is about using 3-point statistics to control systematic uncertainties in future weak lensing surveys like Euclid. So what I'm going to talk about is, first of all, the motivation for doing this work at all. Why use 3-point statistics? I'll then talk about the systematic uncertainties that we looked at and some of the background to why we chose those. Then I'll go through the modeling methods we used and assumptions and present our results, and conclude with the idea that actually this seems to be quite a promising way forward, a promising alternative to dealing with systematics in the future. So why use 3-point statistics? Most weak lensing analysis up to now has just used 2-point statistics. And here are some results from 2 recent surveys, Kids 1000, Shear 3. And they show the familiar weak lensing banana in the omega matter sigma 8 plane. And they're based on 2-point statistics. In fact, the kids analysis here is based on 3 different 2-point statistics. And all these results are very good. They're excellent, good constraints. And why would you want to complicate matters by using 3-point statistics? Well, in the past, people have indeed tried to use 3-point statistics, but mostly to reduce statistical errors. And this is a rather old study by Sembolini et al., where they did actually measure a 3-point weak lensing signal and used it to constrain parameters and found an improvement, although it's really hard to see it by eye in these plots. And that's what you'd expect, because the weak lensing field isn't Gaussian, and you would expect there to be some extra information in higher order statistics. But statistical errors aren't really the issue now, because we're going to have surveys like Euclid and LSST, and they will measure the shapes of billions of galaxies for weak lensing and cover huge fractions of the sky, and statistical errors will be hugely reduced. However, systematic errors will remain, and there are some really problematic systematic errors for weak lensing, which are very difficult to control. And our question is, can 3-point statistics help with these? And one of the reasons for considering this is, if you can use 3-point statistics like bispectrum, you can actually measure them from the same data as you measure your 2-point statistics. In other words, you can self-calibrate without using any external data, and that will be very helpful. So the 3 systematics that we looked at, which are all very important for weak lensing, are first of all redshift uncertainties. Now, these are almost inevitable in a survey like Euclid, because we haven't got spectroscopic redshifts for all the galaxies. We can't possibly do that. So however well you calibrate and model your redshifts, there is inevitably going to be some uncertainty about which redshift bin to allocate galaxies to. Similarly, multiplicative bias, which is the second systematic we looked at. This is pervasive and very difficult to avoid. Some multiplicative bias can arise from things like telescope optics, or from poor modeling of the point spread function. And obviously these can be improved and have been improved. But in the end, you're going to make a nonlinear transformation from pixelated images to measurements of ellipticity. And that inevitably introduces multiplicative bias. And finally, we looked at intrinsic alignments of galaxies. And I'll say a little bit more about that, because it's a bit more complicated for the bispectrum than the power spectrum. So intrinsic alignments are a problem for weak lensing because they contaminate and mimic the lensing signal. When we're measuring lensing, cosmic shear, we're looking for very subtle alignments of lensed galaxies from which the photons are passed through similar matter structures along the line of sight. So the red galaxies here are a source galaxy. It's nothing to do with it being elliptical. And it's aligned by a matter structure of some sort along the line of sight. But so too is this blue galaxy, which is physically close to the structure and is lined by gravitational tidal effects. So if you measure a 2-point statistic, you get 2 extra terms. You get a lensing signal, and you also get what we call GI and II, and GI is lensing intrinsic, and II is an intrinsic correlation. And you need to disentangle these from the pure lensing signal. I explained that in quite a lot of detail because the situation for 3-point statistics is even more complicated because there are many more configurations of source galaxies and intrinsically aligned galaxies. And this means that in the end, we have 3 extra terms in the measured signal if you look at the bispectrum. And each of these 3 terms is a product of the correlation of 3 things. So we get GGI, GII, and III. The helpful thing about this is that the intrinsic alignment affects the bispectrum differently from the power spectrum. And that might be good if you're trying to disentangle the effect. So those are the systematics that we chose to look at. I'll now say a little bit about the modeling choices and assumptions we made. Throughout, we assumed a Euclid-like survey in all respects, but we chose to use only 5 tomographic bins. That's probably an unnecessary simplification in practice for something like Euclid, where you could use 10 or even 20 bins when measuring the power spectrum. So we are actually throwing away information about the power spectrum. Equally, we simplified the bispectrum and so threw away some information because we only used equilateral triangles. And both those simplifications helped with the estimation of the covariance matrix, the bispectrum covariance, because that's really very complicated. And we also looked at this in quite a lot of detail and decided that we could discard the in-survey non-Gaussian terms from the covariance, just use the Gaussian and supersample terms. And finally, as a simplification or a narrowing down of our analysis, we just looked at 2 sets of cosmological parameters, omega matter and sigma 8, and 2 dark energy parameters. We then had a philosophy of basically using standard, tried and trusted methods. So we used Fisher matrix forecasting, where our data vector is either the power spectrum alone or the power spectrum and the bispectrum. And from that Fisher matrix, we define a figure of merit, again, fairly standard. The figure of merit quantifies the information that we have about a pair of cosmological parameters. And so if there are systematics present, that will reduce the figure of merit. Whereas if we can mitigate the figure of merit, then if we can mitigate the systematics, then we can increase the figure of merit. Having decided on this methodology, we need to model the systematic effects. And again, we did this in very simple ways and standard ways, which have been used in other surveys. So for redshift uncertainties, we wrap up all the uncertainty into a single parameter per bin, which is actually the uncertainty in the peak of the redshift distribution in that bin. So we have 5 free parameters, 1 for each redshift bin. For multiplicative bias, we assume that the bias is independent between bins and uncorrelated. And And again, that gives you 5 free parameters, 1 per bin. Intrinsic alignments are a little bit more complicated. We assume that we use the nonlinear alignment model, which is fairly standard. And this essentially assumes that in Fourier space, the field which produces the intrinsic alignment is related to the matter density contrast at the time that the galaxy was formed. And this gives rise to a factor which we called FIA, which can be parameterized, or we parameterize with 2 free parameters, an amplitude and a redshift dependence. So again, fairly standard. Now, the way that we use this information, where we use the figures of merit, is to consider what happens to them when we vary the priors on our nuisance parameters. And in order to self-calibrate, we don't want to have a prior, or we want to have a wide prior on our nuisance parameters. But nevertheless, we don't want to lose too much information. Normally, you would want a tight prior to constrain the figure of merit. So if you consider what happens if you start with a very wide prior and then narrow it, at first, the figure of merit doesn't change very much because one wide prior is just as uninformative as another. As you tighten the prior more, the figure of merit starts to rise quite sharply. And then eventually it becomes so tight that the figure of merit is constrained by the prior completely, and tightening the prior anymore just, again, doesn't have any effect. And what you want is to be in this self-calibration regime, which we arbitrarily a bit defined as a 5%, the region where the figure of merit was within 5% of what it would be with a wide prior. And so we want to be able to self-calibrate. We want to be able to use a wide prior, but not lose too much information. We want the self-calibration region to extend as far as it can to the left. And we want the step up between the wide prior and the plateau here, which is the highest the figure of merit can be. We want that step to be as small as possible. And if we can do that, then we can self-calibrate. Now, this is a schematic diagram. It's typical shape, but it doesn't represent any real results. But if we look at some of our actual results, we see a similar pattern. And this is for redshift uncertainties. Now, the key comparison to make here is between the dotted lines, which use only the power spectrum, and the solid lines, which use the power spectrum and the bispectrum. And the colors, the different colors are just for the different cosmological parameters. And what you can see here is that when we use the bispectrum, the self-calibration point moves to the left as we wanted, and the step up moves down, which is exactly what we wanted to see. And helpfully, Euclid specifies an accuracy which should be achieved for redshifts, which is this vertical dotted line here. And our self-calibration regime, it more or less coincides with that. So this means that we should be able to self-calibrate without any external calibration data. And we get similar results for multiplicative bias. And again, similar results for intrinsic alignments. Now, if that's all a bit complicated, a simpler way to look at it is this. Here we've simply plotted the size of the figure of merit in different cases. And I've just shown one example, which is dark energy parameters and intrinsic alignments. And the bars at the bottom here show how big the figure of merit would be if you had no systematics. Now, that's obviously not achievable in practice. So we can compare it with what we can actually achieve. First of all, if we use the standard method, which is the power spectrum only, but use a type prior based on some external calibration data. And you can compare that with what we did here, which is use a power spectrum and a bispectrum, but essentially a wide, completely uninformative prior. And you can see that figure of merit is much higher in that case than if you use the standard method with just a power spectrum. So we think that looks very promising, and subject to some further work, it looks like a useful way forward. The further work is mainly about whether the modelling methods we used are sensible, robust. And this especially applies to the intrinsic alignment modelling, and especially for the bispectrum, because that is not sort of well established and needs to be verified, basically. And that's some work I'm doing at the moment, looking at intrinsic alignments in simulations. If that work confirms the modelling work we've done, then probably more work needs to be done to look at more practical estimators which can use an actual survey. We use the power spectrum and the bispectrum because analytically they are easy to use, but they might not be the best thing to use an actual survey. And then the other thing that might be followed up is to consider other systematics, and in particular to go to smaller angular scales, consider systematics due to baryonic effects, which are another problem for weak lensing. However, in summary, we think that this is actually quite a promising way forward. Systematics are a key challenge for next generation weak lensing surveys, and it's useful to look at other ways of dealing with them. It would seem intuitive that systematics affect the power spectrum and bispectrum differently, and our modelling suggests that is in fact the case. And our modelling and results also suggest that the bispectrum can allow self-calibration. You don't need external data to set your priors. So we think that this is worth pursuing. It could lead to a practical alternative method, and we are pursuing some more further work to verify that this is a possible way forward. Thank you very much for listening, and that's the end of my talk.